presentation, we're going to hear it straight from the horse's mouth. Professor Garret Moddel teaches electrical, computer, and energy engineering at the University of Colorado, where he also directs the Quantum Engineering Laboratory. From his academic position, he explains that research into these new energy technologies is virtually non-existent. Government and corporate sponsors do not want to take any risks on this kind of research. In addition, they do not wish to be exposed to the giggle factor, which keeps their minds tightly closed. On the other hand, Professor Moddel says we cannot go on chasing after windmills without any real scientific scrutiny. As a recent president of the Society for Scientific Exploration, he walks in both worlds, and he's going to give us a pragmatic view of the new energy technology research and its potentials. Please welcome Professor Garret Moddel.
Thank you very much. I'd like to give special thanks to the GlobalBEM people because you folks have done an amazing job in setting up this conference, particularly under adverse circumstances. And congratulations to you. Thanks in particular to Jerome and Robert and Stephanie and all the GlobalBEM folks. So when my brother and sister were little, they went up to my mother and they said, "Mommy, Mommy, Mommy, are there angels?" And my mother said, "Well, some people believe there are and some believe there aren't. If you're religious, you might believe they are, and if you're spiritual, you might believe they are, if you're agnostic." And so they were looking at her puzzled. So then they went up to my father and they said, "Daddy, Daddy, are there angels?" And he said, "Yes." So from then on, of course, they went to my father to ask questions. And why I raise that is that I'm afraid that what I'm going to be presenting to you is more like what my mother said. It's nuanced, it's in between, and it's a little different than perhaps some of the other speakers who have very definite answers. And so I have some answers, but a lot of questions. So where are we here in terms of new energy research? I believe that we are, and I am in particular, between the stuffed shirts and the crackpots. So my colleagues at the university and I are stuffed shirts. We think that this maverick stuff is crazy. On the other hand, my colleagues here and my maverick scientists here think that the people that the university people are stuffed shirts and don't really understand what this new technology and these new concepts are about because they're stuck in an old paradigm. And so we're in this difficult situation where if you look at research at universities, it tends to be very conservative. And it's a conservative for good reasons, because the conservative science works to a degree, but there are some problems with it. So today, what I'd like to try to figure out with you is, to some degree, where is the truth? Is the truth where, and so in doing this, we'll take a look at where good thinkers go wrong, what physical law tells us, and in particular, we'll look at two laws, the second law of thermodynamics and the conservation of energy. And we'll also look at what physical law doesn't tell us. Where might these physical laws be lacking, and where is there room in our current understanding of science for these developments in new energy technologies? And then finally, we'll talk a bit about what the issues are in new energy technology and what we might improve, particularly from an academic or a more scientific point of view. So you're asking the question, where am I coming from? Is this guy with us or is he against us? So let me give you a little, just a very quick background. So my stuffed shirt background is I was educated in mainstream engineering and physics. I have graduate degrees in applied physics. I worked and ran several high-tech startup companies. I raised quite a bit of venture capital money and had some companies that were where the technology was quite successful. I've carried out research in my lab in liquid crystal technology and dominantly in solar cell technology. And the courses I teach are a group of courses including thermodynamics, statistical thermodynamics, theory of solid state, and so on. From the maverick or crackpot perspective, I've been going in new directions, particularly in this latter part of my career. I decided really it's worth taking a look at what genuinely makes a difference. And so my lab is looking at new types of solar cells. We're working right now on rectenna solar cells, which is an exotic new type of technology. We actually just came out with a book on it last week. We've been working in the lab on zero-point energy extraction, low-energy nuclear reaction. We've also done a fair bit of psi research, and right now I'm teaching a course this semester called Edges of Science, in which we look at maverick science and we look at new ideas and where they fit, what is the philosophy behind this, and beyond. Okay, so what is the issues with science and where it's gone? If we look in the past, if we look a couple of hundred years ago, we see that science and its pursuit was very different from what it is today. A couple hundred years ago, people looked at big questions. Is there evolution? Is there a relationship between force and acceleration? And they tackled these big questions, and the people who tackled it out of curiosity. They were non-professionals. Usually they were from some wealthy family or for some other reason had a benefactor that allowed them to pursue this. But it was curiosity-driven science trying to uncover the big questions. And the answers that they found were often unexpected because it was curiosity-driven. If you compare that to the mainstream science today, it's very different. Today, the questions we ask are little questions. What is this effect? How can I nudge this idea a little bit farther? If you look, for example, in a number of different organizations, the American Physical Society or the IEEE, electrical engineers, and every decade or so they come out, what are the questions that are remaining? And if you look at those questions, if you're like me, you see that those questions are little questions. Why is this effect this way and not that way? Why doesn't symmetry apply here? Rather than the big questions that we still have, why is the universe this way? Are there sorts of energies that we just haven't accessed? What is the connection between people that goes beyond just our brains? What are the subtle things that are happening? These questions aren't asked. And part of it has to do with the government funding, because in government funding, if we want to get a contract, we've got to say what we're going to look at, what we're going to discover, and when. And so if we already know it before we've started, we're obviously not going to do anything very dramatic. And what this does is it builds very successful careers. If you continue to look at a particular small phenomenon, but you become the world expert in that phenomenon, you'll be great. You'll bring in lots of government contracts, you'll do a good job training students, and you'll be successful. But the answers that you'll get will be fairly predictable. And I think we're, in this group here, I think we realize the distinction between the unexpected answers and the predictable answers. So what are the problems? Well, there are several different problems that cause us to remain fixed in a situation where we're looking at the same answers over and over. And one of these is information cascades. So information cascades occur when an expert gives an erroneous opinion. And once that expert has given an erroneous opinion, many people afterwards, even if they've got the right information and want to give an opinion that is correct, nobody listens because the expert has already spoken, and it's very hard to change this. So the classic example, which I show here as a picture on Time magazine, is a physiologist, Ansel Keys. And in the 1950s, looking at a partial study he saw that there appeared to be less heart disease among one population that ate less fat compared to another population, a different country, that ate more fat. So he said fat is bad. And if we want to be healthy, we should not eat fat. And so that became a doctrine. And it was folded into the food pyramid that the government told us is the right thing to do and the right thing to eat. And this idea that fat is bad in the diet and causes heart disease and cancer lasted for more than 50 years beyond when Ansel Keys said it. And he was wrong. He was wrong right at the beginning. In fact, even the study that he quoted, if you looked at the complete study, it showed that, in fact, fat is good. Particularly, there are all sorts of good fats that we should be eating, and it's sugars and simple starches that are the problem. But this problem just kept compounding, and so everybody, until very recently, has been believed this incorrect information cascade. And only in the last few years are we finally saying out loud, look, fat is good for you. And there are other examples of information cascades. There are many, many of them. Another one is fluoridation, and that fluoridation is good for our teeth and not harmful to us, which is wrong. Another one is sun exposure, that we should avoid all sun exposure. It gives us cancer. No, sun exposure is good for us, and there's all sorts of evidence for it. We don't want to go and burn ourselves, but moderate sun exposure is definitely good. And there are many of these. And I believe that new energy also falls into one of these information cascades. There's another issue, and that has to do with consensus. Let me just read what Michael Crichton wrote. The work of science has nothing to do with consensus. If it's consensus, it isn't science. If it's science, it isn't consensus. Also, he wrote, consensus is invoked only in situations where the science is not solid enough. So how many times have you read in the paper, the majority of scientists believe this, or the majority of scientists believe that? It happens all over the place. And the only way to break this, as Kuhn has taught us, is with a scientific revolution. And so we have a particular paradigm. We break out of that paradigm after enough information accumulates. And it's usually literally a generation, 60 years or more, after the initial incorrect information was believed by the consensus. And there are many examples of consensus science. Galileo's heliocentric solar system, Wegener's continental drift. For between 1920s, when Wegener said it, until the 1960s, geologists wouldn't believe him, despite the fact he had robust evidence to show that there was continental drift. Evolution through natural selection. So we've got Darwin, who's been accepted by the consensus. Then there's Wallace, who had a slightly different view. And some of us think maybe that's a little more appropriate. There's anthropogenic climate change, where we read over and over in the paper that 90-something% of scientists believe something or other. I'm not saying it's wrong or right, but what's happening here is that the consensus idea is invoked rather than the basic truth of the matter. And science has become very political because of that. So what do? We've got to look at the data and think for ourselves. And that's very difficult, because a lot of this data is complicated, and we just don't have the time for it. And so we find somebody who we believe, and we just stick with them, which is sometimes okay and sometimes it's not. As Einstein said, innovation, the important thing is not to stop questioning, and we've got to keep doing that, despite the consensus. Okay, so what can we believe? So we've already said that in mainstream research, there is incremental advances. They're slow to provide breakthroughs. We've also learned that experts provide opinions. Often they're right, but quite often they're wrong. And so then we are subject to information cascades. The truth doesn't get out. Consensus science is often wrong. And in fact, not only is it often wrong, but we know that the current paradigm will go through a revolution. It always does. It has in the past. And it's only arrogance if we say that today's standard model is the one that's going to exist in 100 years. Of course it's not. We're going to think of new things. So does that mean that we should throw out established physics? No. Established physics has a lot of wisdom to it. We need to use it but we need to carefully see where it applies and where there are holes. What we need to look at, if we're looking at new sciences, we need replication, we need coherent explanations, and what we're talking about in particular here is we need consistent energy production. And we found that with a lot of these technologies, we've got some of this, but not all of it. We need to work through and get all of it. Okay, so enough for the sociology of this. Let's get on to the science. I've been approached over the years by a number of people with various sorts of ideas for new energy technologies. And I've found different sorts of issues that people have not considered in a way that I think is appropriate. So one of them, and this has happened repeatedly, you've probably seen it. Somebody has some sort of a motor or an electric circuit that produces more power out than is required to go in. And so what they do is you measure the voltage out and the current out, and you multiply the voltage by the current, that tells you the power, and you compare that to the power in. So if we have a time-varying signal, and this is the voltage, this is the current, so the power is the voltage times the current, and it's positive. And so we get a net positive out. But what happens a number of times is that people don't measure the voltage and the current together in the same way, and they don't look at the phase relationship. So if you've got a voltage that varies like this blue signal, and a current that's 90 degrees out of phase from it, if you multiply the voltage by the current, you're going to get power, but it'll have a positive part and a negative part. And the ultimate, the average power that comes out is equal to 0 in this particular case. So we've got to look at this. And we, and I'm including myself here in the maverick scientists, make errors quite often in looking at these sorts of phenomena and trying to decide, is there more energy out or is there more energy in? Here's one I was sent, maybe 4 or 5 months ago. Somebody sent me their plans for a Brownian motor. The basic idea, it's a little wedge-shaped gap. And inside this gap, we've got a particle. So imagine this is a gas particle or something like that. And there are actually many of them, but let's just look at one to begin with. And so the gas particle has thermal energy and it bounces around. Now because this wall is sloped compared with this wall, every time the particle bounces up, it'll tend to move to the left because there'll be a net motion. It'll bounce a little bit net to the left. And so eventually, it'll go all the way to the left. Now, if you compare the front to the back, you can make a circular type of wedge. And in this case, if it's always going to the biggest part of the wedge, and then here it goes through again and comes back around, what you can do is you can get perpetual motion. And you can get the machine going around, you can get the particles going around and around, and it should give you motion without any energy input. And if you've got a lot of particles, well, that lot of particles should be going around, and in fact, maybe you can make the wheel go around, and you can get energy out without energy in. Will this work? No. Why will it not work? Because there's a counteracting force. And that is that when you gather a lot of particles on one side, you've got a higher concentration here than you do here. And what you end up with is a diffusion gradient. And the diffusion gradient causes particles to diffuse this way. So they move to in the counterclockwise direction by bouncing, and they move in the clockwise direction by diffusion, and the net motion is null. And we see this in all sorts of phenomena where there's some sort of a driving force, but then it's counteracted by some sort of another force. So this folds into the second law of thermodynamics. And there are many ways of saying the second law of thermodynamics. I'm going to mention this particular one here because I think it's most appropriate for what we'll be talking about with the energy technologies. And that is, it is impossible to convert heat from a system at constant temperature into work. It wasn't actually Moses who said this, but that doesn't matter. And so this is really one of the fundamental laws. It was so fundamental that Einstein has said classical thermodynamics is the only physical theory of universal content which I'm convinced will never be overthrown. So let's take a look at some of the ramifications of the second law of thermodynamics and see whether we agree with this law or not, and if we're allowed to violate it. So before I do, I want to say that when I was a graduate student at Harvard, I went to my professor once, and he wanted to hear about the experiment I was doing. I was working on solar cells and a particular semiconductor. And he said, well, how does this process work? And I said, well, the electrons go here, and because of conservation of electrons, they've got to go here, and so this reaction is balanced by this reaction, and it's got to be equal. They've got to be equal. And he said, no, how does it work? And I said, well, there's no net production of electrons, so they've got to be equal. And he said, no, tell me how it works. And he used to slam his fist on the table quite a bit until he had his quadruple bypass. But to his credit, he let us yell back at him. He was actually a great professor. And I realized at that point that he was asking for a kinetic answer. He wanted to know this pushes this, this pushes this. And instead, I was giving him an answer based on a conservation law, conservation of number of electrons. And so we'll see that in physical law, there are often two ways of looking at things, the kinetic way and the conservation way. And both of these should tell us the same story, but sometimes they contradict each other. And let's go on and take a look. So with the second law of thermodynamics, Maxwell proposed in 1871 a demon. And the purpose of the demon was to try to find holes in the second law of thermodynamics. And the way that this demon works, the simplest way, is imagine you've got a chamber with gas particles in it. And what the demon does is whenever a hot gas particle comes along, going from right to left, he opens the door, he closes the door and doesn't let it go. Whenever a hot particle comes from left to right, he opens the door and lets it go through. And cold particles just the opposite. And so that way you eventually end up with a bunch of heat on one side, a hot gas on the other side, and a cold gas on the other. And once you've got this difference in temperature, or it could be pressure, you can do work with it. And so this is a way of getting work out of the ambient background. And so he said, is there a way for this demon to work? And physicists have argued about this for more than 100 years. And there have been all sorts of demons proposed, and all sorts of solutions showing that, in fact, the demon doesn't work. And the latest has to do with, over the last couple of decades, it's become pretty clear that the basic issue has to do with information, surprisingly, not energy. That there's a sort of a conservation of information and an entropy of information. And that basically determines why the demon cannot work. Unfortunately, I don't have time to go into it in detail right now, but let's just leave it at that. So where are examples where we might like to have a demon work? One example is using a diode to obtain electrical power from ambient thermal fluctuations. So a diode, for those of you who don't know, is an electronic device that allows current to go in one direction but not in another. And I'm showing a band diagram for a diode. If you don't understand this, don't worry. That's not crucial here. But the basic idea is that we have thermal generation. So we get an electron moving from the valence band up to the conduction band. Then it drifts down this potential barrier, and we collect it externally using an external circuit. And so that idea then should be able to take thermal fluctuations and convert them into work. And there have been a number of proposals for this, but in fact, I believe it doesn't work. And the reason has to do with detail balance. So detail balance, which was proposed in the early 20th century by Einstein to describe radiation and elements in equilibrium, says that for every up, there needs to be a down. For every down, there needs to be an up. and that is that every action is balanced in detail by its opposite when we're in equilibrium. And so that would say that under thermal equilibrium, that means, in other words, just this diode sitting in thermal equilibrium, there will be a generation rate due to the heat, but there will be an equal recombination rate, and you're not going to get any energy out. So what sort of argument is this? Well, the basic argument is one of the second law of thermodynamics. So that's that sort of a conservation equilibrium approach. Then the detailed balance is instead a kinetic argument. And so both by the kinetic argument and by the conservation argument, we say, no, we can't get energy out from a diode at equilibrium. Well, there are some people who will disagree with that. In fact, people at this conference. And I've looked in some detail at the papers that suggest that, in fact, you can get energy out. And what they do is they make a kinetic argument, saying that, yes, you can get energy out because this causes this, which causes this, which causes this, and a fairly detailed argument. And I believe that when there's an argument between a conservation argument and a kinetic argument, which of the two do you believe? I would go back with the conservation argument, because with kinetic arguments, there's a lot of details and it's easy to make a mistake. But it's possible that that's not right. So how do you ultimately know which one is right? Well, the answer is, of course, experiment. Because experiment trumps theory all the time. And if you actually get something to work, hell, you've got it to work. Don't worry about the theory. Okay, so is the second law of thermodynamics always valid? Well, we know that the consensus of physicists says yes. It was originally a statement of collective experience, and then later it was codified into a detailed explanation, statistical explanation for gases in equilibrium. And so that seems to say, yes, the law works, because the consensus of physicists agree with it. But do we think that the consensus of science is always right? Well, here I've got to give a nuanced answer. There are very serious questions about the second law, not only among maverick scientists, but even among more mainstream scientists. And there was a conference run by Daniel Sheehan a couple of times taking a look at, does the second law always apply or not? And in particular, I can say with a pretty strong degree of confidence that if you're near equilibrium, if everything is more or less at the same temperature and stationary, yes, it applies. If we're in a closed system where there's no interaction and we're at equilibrium, then it applies. But where it doesn't apply, where we've got lots of wiggle room, is if we're far from equilibrium, if there's a fast changing system, something with radical temperature differences. And so if we look at the sorts of motors and circuits and various other devices that we've seen here, the ones that seem to be putting out extra energy are those that are far from equilibrium. And finally, open systems. What does an open system mean? It means that we've got an interaction with the external world. Well, can we have a closed system? No, we can't really have any closed system, because there's always going to be interaction with gravity outside. We don't have a way to block it. There are always interactions with zero-point energy and various other things. So systems are, in fact, open. Let's take a look at this next law, which is conservation of energy. So we know that this says that the total energy of a closed system does not change. So if I'm cold standing up here and I do mechanical work on my hands, that work is turned into heat. And so the work of my muscles and the energy produced by my muscles isn't lost, it's turned into heat. So it's been conserved. Energy has been transformed from one type to another, but it's been conserved. Well, actually not too long ago, somebody sent me some information on a way he said was a very simple way of showing that conservation of energy doesn't work. And this is the argument he made. And this is going to get a little bit mathematical. So for those of you who are allergic to that, please hold your nose. But for the rest of us, it's not going to be that hard. So we know that so this is the argument that I was given. We know that Newton's law says that force equals mass times acceleration. And we can solve that for acceleration to say that acceleration equals force divided by mass. Now, imagine that you have some sort of an object in free space and you push it. So you're going to push it with a given force. It's going to accelerate and go faster and faster, okay? And that's the example that's given. So if we take a look at the kinetic energy of the object, the kinetic energy of the object is 1/2 times the mass times the velocity squared. And that's a non-relativistic formula for kinetic energy. And so we can write that instead as 1/2 times mass times acceleration times time squared, because velocity equals acceleration times time, so we can just rewrite it this way. And we had solved for acceleration up here, so we can stick that in which case the formula becomes 1/2 times the force squared times time squared over mass. And so the argument here is that when you're applying a constant force to an accelerating object, the energy is going to increase quadratically with time. It's going to increase with the square of time. And so the argument is that the kinetic energy is proportional to t squared, but the input force is constant. So if we look at the cumulative energy required to maintain a constant force, so this is energy versus time, it just grows linearly with time. But if we look at the kinetic energy of the accelerated object, it grows with the square, with t squared, time squared. And therefore, eventually, it's going to exceed the energy that you put in there. And energy is no longer conserved. Do you see the flaw in the ointment? Fly in the ointment? So the idea here then is that the accelerating body gains more energy than provided by force. We've got new energy. But maintaining a constant force on an accelerating object requires going faster and faster. And in fact, the cumulative energy that you put in to give a constant force to an accelerating object varies with the square of time. And it turns out then that both the energy you put in and the energy of the object increase with the square of time, and the cumulative energy is equal to the kinetic energy. We didn't gain any energy. And so energy is conserved. So that's an example of where we need to think about something a little bit more clearly. Let's talk about open systems, which I mentioned before. So one of the sources for energy in an open system that I'm most interested in is zero-point energy. So according to the Heisenberg uncertainty principle, we cannot know the position and the momentum or the motion of a particle to absolute precision at the same time. So we cannot have a particle that sits still, because if it sat still, that would mean we'd know where it is and how fast it's moving. So therefore, according to quantum mechanics, all particles are moving all the time, no matter what, and that's zero-point energy. Not only are particles moving all the time, but space itself wiggles. So in particular, if we look at electromagnetic waves, there are constantly electromagnetic waves that are bipping into existence in the vacuum. And these waves that bip into existence in the vacuum are part of the zero-point field, ZPF. And if we take a look at the formula for radiation, that is electromagnetic radiation that we find in the air, there are two parts to it. One has to do with the temperature, and this is T for temperature, and another part has nothing to do with the temperature. This is the thermal radiation, it's the Planck distribution, and this is the zero-point energy radiation. And so both of them exist at the same time. And if we look in free space, if we go above a frequency of 7 terahertz, at that point the zero-point energy dominates over thermal energy for room temperature. Okay, so if we have this zero-point energy, can we use it? Is it really real? And many of us have seen the concept of a Casimir cavity, where we in fact can show that it is real. So a Casimir cavity consists of two plates that are reflective, that are very close to each other. And because those two plates are very close to each other, because of boundary conditions, they block some of the waves inside. We can only have a restricted set of waves inside the Casimir cavity. But outside the Casimir cavity, we can have the full spectrum of waves. So therefore, if we look at the radiation pressure due to the waves pushing on the walls of the cavity, we'll see that there's more radiation pressure pushing in than there is radiation pressure pushing out. And the net effect is that the cavity collapses. The two cavity walls are put together. This was proposed in 1948 by Casimir, and over the last few decades, people have measured this to increasing precision and found, yes, in fact, there is a Casimir force and you can measure it. So this is one indication that zero-point energy is real. So can we use this? There have been various proposals to get mechanical work out of a Casimir cavity. And one of these is this one. So let's say that we have a Casimir cavity with a certain spacing between the two plates. We then allow one plate to, we move to the other plate. We allow the plates to collapse. And when the plates collapse and go together, they produce work. And we take that out as work. And it's in fact been shown that we can get electrical energy out and all sorts from this Casimir cavity. So we really can do work on this. Whoops, what happened here? Okay. So I'll talk until it comes back up. So the idea is we have these Casimir plates that have moved together. Now we do something to disable one of the plates. Let's say we take all the electrical charge out of the plates. And so we take all the electrical charge out of the plates, and then we pull the plates apart. We can do it without expending any energy because we've disabled the plates. After we've disabled them, we let the plates come together again and once again give us some conversion of zero-point energy into work. And so this has been proposed, and the basic idea here is that this will work under one condition. And that one condition is if the Casimir force is not conservative. So let me give you an example of a conservative force. Gravity. So if I have a bottle of water and I let it fall, I can get work out of it. But I can only get work out of it once. Then if I lift up my bottle of water to try to get work out of it again, I've put the work that I got out of it back into it to lift it up. Why? Because gravity is a conservative force. So the question is the Casimir force a conservative force? And there's been a fair bit of work on this, and in fact, it turns out that it is a conservative force. Therefore, I would say you cannot get energy out of a Casimir motor. Now, there have been arguments against this. I went through a paper yesterday. I reread a paper that proposed about 15 years ago to be able to make a Casimir engine that would produce work. And in fact, the paper is based on a kinetic argument. Remember kinetic argument versus conservation law? And so it shows that if you take the charge out of a semiconductor and you let the material go together, this will happen and this will happen. And it's a very complex argument. And I think there's a fair potential in it for some errors. And in fact, as we learn more about Casimir force, we're learning more and more that in fact Casimir force has some strange properties. And so I don't think that we can get work out of a Casimir force. And so I think that this Casimir engine that I showed you with the plates, that in fact when you extract the charge out of the plates, you're going to end up using as much energy as you got out by letting the two Casimir plates go together. Okay, whoops. So about 8 years ago, a guy called Bernie Haish, who is a physicist who lives in California and has worked done quite a bit of theory on zero-point energy, contacted somebody, an acquaintance of both him and mine, and that's Dean Radin. Dean Radin, and he asked Dean, he said, I have this idea of how we can make get energy out of a Casimir engine, or in particular out of zero-point energy. And I'd like to be able to build this. I'm a theorist. You know of some practical physicists who might work with me. And so Dean Radin hooked him up with me, and he and I then put together some practical ideas of how to obtain zero-point energy from the vacuum. And we applied for a patent, and if you could see the slide, it would show you the patent, or at least the front of the patent that we applied for. And surprisingly, the patent was granted. And it issued in 2008. And so let me tell you a little bit about how this works and how we should think about it. So the basic idea is based on a concept, a theory called stochastic electrodynamics. So if we take a look at an electron circling an atom, we know that an electron will go around an atom, and it should be radiating energy because an electron circling an atom is accelerating. An accelerated charge should give radiation. That's called Larmor radiation. And so it should spin down. The electron should spin down to the core of the nucleus of the atom. But it doesn't. Why doesn't it? The real answer is because Bohr said so. So Niels Bohr said it doesn't. And so he built, from that concept, the foundation for quantum mechanics that ended up with the Schrödinger equation and the whole apparatus that we have for quantum mechanics, based upon the idea that energy can only be radiated in quanta, and that there's a reason that this cannot be radiated. And so there is a different explanation. And the different explanation is from stochastic electrodynamics, which was actually started by Einstein and Otto and others who were not particularly in favor of quantum mechanical explanations for things. And what they said was, yes, in fact, the electron circling the atom does radiate, and it does spin down. The only reason that it doesn't spin down all the time is that that radiation is being balanced by zero-point energy radiation that's coming in. So there's a net balance between the incoming radiation and the outgoing radiation. And so this is the concept in stochastic electrodynamics, that in fact the atomic structure is based upon zero-point energy. And the whole world actually stands on it. It supplies the energy that keeps the atoms energized. And there have been tests of this. There's been a theory that showed, in fact, it works. There's also been simulations showing that you get the exact correct radius for the Bohr atom, for the electron circling the atom, if you've got this balance of zero-point energy versus coming in versus the radiation going out. So I wish I could show it to you, but our basic concept is that we take gas atoms and we pump them into a Casimir cavity. As they're going into the Casimir cavity, they are going to spin down to a lower energy because a Casimir cavity has less energy, less zero-point energy inside than outside. So it'll reach a new equilibrium inside the Casimir cavity. As the electron spins down, it radiates energy. We capture that energy. Then, when the electron comes out of the Casimir cavity, it's recharged back up to the ambient, by the ambient zero-point field. And so in this way, what we've built is essentially a heat pump in which we extract zero-point energy from the ambient, and we then deposit it into a local heat source. And we can use the heat, or we can convert it into electricity. Now you ask, wait a minute, this doesn't make sense because isn't the zero-point field the lowest energy possible? So how can you get to a lower energy in order to extract energy from the thing in equilibrium? And the answer is that, in fact, it's geometry dependent. So if we look at a Casimir cavity, the floor is lower than the floor is outside of the Casimir cavity. And we do, in fact, have a difference in energy between the ambient area and inside the Casimir cavity. And this allows us to actually extract energy. And so we've built some practical, have some practical designs for prototypes that should work. We've also built quite a few of these and tested them. And again, I wish I could show you this. We've got a plot which shows the energy radiated from these Casimir cavities as a function of gas and as a function of gas flow. And we find that, in fact, oh, great. So this is the plot. So let's go back into slide mode. Where do I do that? Top left. And so this shows that we, in fact, do get energy out. However, I have to say that I'm not yet convinced that this proves we've obtained zero-point energy. We've got to go through and figure out, is there any other possible explanation for it? We've done a fair bit of that. We've vetted it and found that conventional things like Joule-Thomson cooling and various other things just don't work. But we need further work in order to draw firm conclusions. So there are problems with zero-point energy and all sorts of new energy research, and we all know this. One of the big problems is secrecy. If we keep our ideas secret because we want to become a zillionaire and don't want the rest of the world to know about it, or because we're afraid somebody's going to zap us, then we can't really work that way. And so a way to get around the secrecy is live open science, which is one proposed idea for sharing information when we're doing experiments. And I think a new energy field is a great way to do it. There's the idea that if we could develop new energy technologies, we should just give it away, give it to the world. In my opinion, that's a bad idea. The reason is that it takes a fair bit of effort to go from a basic concept into a well-developed technology. And there needs to be incentive for people to do that. And so there needs to be some profit motive to drive them. And I think that we can give it away once it's developed. But in the development phase, I think there needs to be some incentives. Another problem has to do with blind skeptics. So perhaps that's, you'd say, the stuffed shirts. And if we look, for example, at the example of Galileo, where people from the church refused to even look into his telescope, we find the same sort of things today, where science journals absolutely refuse to publish anything on cold fusion, no matter how good the article is. They just will not. And this is very much like the blinders, I think, that the church has put on. And so we need replication, coherent explanations, consistent energy production. The other problem from the, perhaps we can call it the mavericks or the crackpots, is true belief. And if you believe something, then everything you see will look like what you believe due to confirmation bias in what we see. And so we've got to really be our own toughest critics. So how do we work through this? Well, I think one great idea is what Joel Garbon said a couple of days ago, the idea of some sort of almost like a UL testing lab for new energy technologies. And we need to be able to test these things, have them vetted, have a group that say, yes, this really does work, or it doesn't work. But I think we need something before that as well. And the something before that is a real digging into the technology from the perspective of curiosity and, yes, even academia. And so one thing that I'm suggesting and proposing is that we develop a lab at the University of Colorado called the Breakthrough Energy Technology Initiative. And it... I'll tell you, that's the most positive response I've had. Thank you. And the idea here is we're not a debunking lab. I don't even like the word debunking. We are an advocate. We're going to be looking at these new technologies and digging in. We want to understand how they work. So, for instance, each technology that we choose would be assigned to a particular grad student who spends, 4 or 5 years digging deep into it, try to understand it, try to make it work. And we want to nurture these technologies. This is going to require very dedicated students with excellent skills. This is really something that's going to be hard to do. We need also major donors. It's going to be expensive. But I think that the result of something like this could really separate the wheat from the chaff from all these technologies, because so many of them really could be working, but yet we don't know, is it working or is there something subtle happening here that's causing it not to work? And we really need to dig in and figure this out. So there you have it, my views. I think you may agree with some of them, may disagree with some of them, and I'd love to talk with you folks about it later. Thank you.